Hello Internet. This video is about velocity and acceleration. We're going to discuss them mostly conceptually, but I'll throw in a little calculus to help, if that helps. So the most important thing to remember about velocity and acceleration is that they are vectors. This means that they have magnitude and direction. Now, I say it's the most important thing in that it's easy to forget, and it can really mess you up when you do. So just remember that they are vectors. Now, I'm going to talk about the magnitude of velocity, which I just call v, and the magnitude of acceleration, a. In this video, vectors are discussed elsewhere. So, the magnitude of velocity is simply distance over time, which you already know, I'm sure, because, well, this could be in miles per hour, or kilometers per hour, or whatever you prefer. In physics, we prefer meters per second, because our equations are set up to require meters per second, many of them. Move that up here. Now, in calculus terms, velocity is the derivative of displacement with respect to time. Now, that actually makes sense, because if you have distance over time, well, that is a rate of change, and the derivative gives us an instantaneous rate. To refresh your memory, if we have x versus t, for some particle, like, I don't know, a train, a car, something moving in a straight line, well, say it's moving forward, and then it moves back, and it's moving forward. So it's got some function of position versus time. If we want to know its velocity, well, the velocity is going to be the slope at any given point here. And the slope is, the instantaneous slope, is the derivative. So if we have a function, we often don't, but if we do have a function for x, say it's like some function, we can find the velocity because we know, well, velocity is the derivative of x with respect to t. And in this case that I just made up, I guess that's 14t plus 8. Alright, so the magnitude of velocity is distance over time, and that is the derivative of the distance versus time function. Now, acceleration. Acceleration is something that you might not be quite as familiar with. There's no accelerometer in your car. There is a speedometer in your car. But acceleration, well, the concept extends nicely. It's going to be the change in velocity over time. If you have positive acceleration, you're getting faster and faster and faster. If you have negative acceleration, you're getting slower and slower and slower. The point is you're changing velocity over time. Like if you were to fall, when you fall down off of a skyscraper, which you probably haven't done, you get faster and faster and faster, and that is acceleration. So it extends from our discussion of velocity that acceleration is the derivative of velocity with respect to time. Now recall that velocity was the derivative of displacement with respect to time. So acceleration can also be written as the second derivative of x. Remember this notation here. It's d squared of x over dt squared. A little strange. So let's just check out one of these graphs. If I have velocity versus time, and it's increasing, decreasing, some kind of velocity function, acceleration will be that instantaneous slope. Wherever you evaluate it. And so if we have a velocity function, like say the one we just finished off with, we can find the acceleration. So acceleration is the derivative of velocity with respect to time, which in that case up here is going to be 14, right? So we actually got a constant acceleration in this case that I made up. And we often do have constant acceleration, but it's not required. There are varying acceleration functions. Alright, so now let's discuss how you might apply some of this to a likely test or homework question. They love, in the first chapter of mechanics, to give you graphs of position and or acceleration and or velocity and have you figure out what the other graphs are. So let's try that out. I'll put a position graph here, a velocity graph here, and an acceleration graph here. So let's say we have a velocity like this. Looks like it started out at some positive value and increased. And it's a straight line. So, well, if velocity is increasing, then I know that there is some acceleration, some positive acceleration. And I know it's going to be moving in the positive direction because it's positive velocity. Now, this reasoning is helpful, but almost unnecessary if you understand calculus. Let's just make up a likely equation for this velocity line. Well, it looks to me like it's just something that I could write in slope-intercept form. V equals some sort of slope. Go with m, like from algebra, times the variable t, plus some initial value of the y-intercept there. Well, I can figure out what acceleration is because I know that acceleration is just the derivative of velocity. And so the derivative of that will be simply m, which is constant. Just some constant value from out there that's positive. And so my acceleration graph is just going to be a boring line, so like so. Position graph could be a little bit tough. Well, we know that velocity is the derivative of position. So if we had position, we would take the derivative to get velocity. In this case, we have the velocity and we want the position graph. So I suppose we need the antiderivative, or the integral. So x is going to be, well, let's see, I suppose it'd be 1/2 mt squared plus bt plus some constant of integration. We'll learn how to deal with those later. But this does tell us the shape of the graph. Now we don't know, for example, where the intercept, the vertical intercept will be, but we do know the general shape. It looks like it's an upward-facing parabola. So let's try something like that. And so here from the velocity graph, we were able to figure out the position and the acceleration graph. Now these are the most common ones, the graphs to see. Constant acceleration, linear increase in velocity, and this quadratic x. But it's not the only ones. Let's try another. So let's say this time we start with the position graph, and it looks like this. Now we've got a linear position in position function. So it'd be some sort of simple slope. And, well, we know all we have to do to get to velocity is take the derivative. So that's like, that'll be m. That's easy. And the acceleration, I'm getting a 0, right? The derivative of a constant, m, is 0. So for velocity, here we had a constant velocity and an acceleration of 0, which I can still graph like that. And so there's another possibility. Now there are many others, but these are probably the most common. And And that's about it for our discussion of velocity and acceleration. Velocity is the change in displacement over time, and acceleration is the change in velocity over time. It's important to recall that they're both vectors, but for this discussion, we mostly concerned ourselves with their magnitudes. Thanks.